तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will continue with the simplification of Boolean functions or logic functions. In the last lecture we talked about Boolean algebra being a set of formulae or identities to be used to simplify a given logic expression without changing the Boolean relationship. That is, for a given set of conditions, input conditions and output is defined as a true or false. So, when you make a simplification, that should not change. Whatever simplifications you make, the output should still be true for all the input combinations for which it is supposed to be true, and should still be false for all the input combinations for which the output is supposed to be false. Now, we will continue this and use a graphical method. As I mentioned earlier, it is not a new technique or anything. I mean, it is not a new theory or anything. It is a systematic procedure actually, if you want to call it, it is a procedure. At best it is a procedure systematized for easy handling, or when the function gets more complicated, bigger and bigger, so that it can be automated also. Because there are other automated reduction techniques other than graph method. We will not see them in this course, but these are all having the same type of concept, namely identify wherever possible the combining of the terms. What did we do yesterday? In order to reduce the or simplify the function, if you can reduce the number of terms, is good, and if in each term if you can reduce the number of variables, it is good. So, we will use the same method to see wherever possible we can combine the terms into a smaller term. Two terms can be combined into a smaller term, then there is a saving in hardware. The same concept will be applied in graph method, and later on there are methods called computerized methods, implicant methods and all that. We will not see those things because conceptually they are same. They are merely procedures. If you know how to do it conceptually, you can learn the procedure anytime depending on your requirement. So, we will start with the map method today. Map method of Boolean simplification. can also call it a graphical method, but usually it is called a map method. What we have to see is, what we have to do is to map the truth table on a graph. Look at the truth table, there are ones and zeros on the output, and we want to combine all these ones together to give the minimum possible solution. Now we will map it on a graph and see whether there is a possibility of combining those. That is all we are going to do. We are going to repeatedly use the same concept of Boolean algebra again and again. There is nothing like we are going to use a different set of equations or identities, the same set of equation identities, but in a systematic way. So let us take the example. So the what is the a map is nothing but all variables are present in a map in true form and complement form. In other words, we will have a value correspond to each input combination that is possible. Let us take an example of 3 variables. Let us say variables are A, B, C. What are the 8 combinations of A, B, C? A bar, B bar, C bar, A bar, B, C bar, A bar, B bar, I mean A bar, B bar, C bar, A bar, B bar, C, etc., finally A, B, C. Now that means there are 8 possible values. So we will now draw a graph with 8 cells. So this is how it is going to look like. You can draw it horizontally and vertically, it does not matter. I need 8 cells in this map. I call this a 3 variable map. Eight cells corresponds to the corresponding to the values A bar, B bar, C bar, A bar, B bar, C, A bar, B, C bar, A bar, B, C, etc. This will be represented here. I will say on this axis the vertical, I will let A vary, true complement value, true value. That means a 0 here means A bar, this cell will have a value of A for this cell is A bar, value of A for this cell is A, and this cell will this on the horizontal axis we will let B and C vary. There are 4 possibilities of B and C varying: B bar, C bar, B bar, C, B, C bar, B, C. So that can be represented by 0, 0, 0, 1, 1, 0, 1, 1, right. So when I say 0, 0 here for B, C, A 0, B 0, C 0 correspond to A bar, B bar, C bar, that is all. Here this will be A, B bar. You do not have to write it later on, anyway. First time I am doing it, so I am writing the corresponding values of the input combinations. Input combination I am writing in the cell, but the cell is supposed to have that combination. Once you are familiar with this, you do not have to write it. Then the next one will be 0, 1 for B and C. So this will be A bar, B bar, C. This will be A, B bar, C. Now what will be the next value for BC? 1, 0 or 1, 1. But if you put 1, 0, what will happen is I have to write A bar, B, C bar. But I would like to have this adjacency rule. Remember, this type of identity I have used to repeatedly to combine a knockoff variable. So for example, if we have A bar, B bar, C, or A bar, B, C, then I can take this as A bar, C and B or B bar and knock it off and write it as A bar, C. That means I should only let one of these 2 variables change. Between B and C, I should let only one of those variables change from cell to cell. From one cell to the next cell, either in the horizontal direction or in the vertical direction. If you let only one variable change and other variable keep its value, then I will be able to combine it with the previous cell. In this case, when you say B bar 0, 1, 1, 0, B changes from 0 to 1, C changes from 1 to 0, both the variables B and C change at the same time. That means it is not possible to combine them effectively. So the technique is then not to write here 1 0 for BC, write here as 1 1. So, BC. So, that means I let B change from 0 to 1, C remain and I let C remain as 1. So, that means this will be A bar BC, this will be ABC, and finally the only other value which you have not used is 1 0, and that means it will be B is 1, C is 0, A bar B C bar, A bar A B C bar. The advantage of this representation is between two adjacent cells either in this direction or in this direction, only one of the variables changes from 0 to 1 or 1 to 0, the other variables remain same. That means I can use this formula repeatedly. This formula A or identity A or A bar is 1 can be used if two adjacent cells are same and both of them are 1, then can combine them to knock off the variable which varies from this to this and retain the other two variables which do not vary from this cell to this cell. The same thing applies here also. See here A only changes, B value C value remain same in all these cases, and this adjacency work also backwards round, it is a wrapping, it is something like a circular symmetry here. So, between this cell and this cell A bar B, B bar C bar C bar, that means B only varies, B is 0 here, 1 here, C is 0 0, A is 0 in both cases. And if we had a 4 variables, 4 columns or 4 rows in the vertical direction, then also I can apply this symmetry in a rotational symmetry. If I had 2 more rows, this and this will be adjacent. So, the cells of this map, I will call each of them as a cell, and cells of the map which are adjacent to each other in horizontal direction or vertical direction will differ in only one variable, all other variables will be same. These are called adjacent cells. Differ in the value of only one variable. Adjacency applies from end to end also, that is what I am trying to say. I am trying to say that adjacency applies from end to end, as if you are folding it around, wrapping it around in a circular way. So, what does it mean now? If I have a value whose output is 1 or true for this case and for this case, that means this will be the truth table will have a 1 in this cell as well as in this cell. When I have 1 and 1 in two adjacent cells of the truth table, I can knock off the variable which is common to, which is different from these two cells and have a simplified expression. That is what we did. For example, yesterday we said we had A bar B bar C bar and A bar B bar C, both of them are 1 in my truth table, I would have written it as so that is what we are going to use in a graphical method. So, we are going to use the identity A plus A bar is equal to 1 repeatedly in the graphical method till we can identify all the groups of 1s and we can do it no more. So, it is a more systematic way of doing it, and you are more or less certain at the end you have exhausted all the possibilities, because it is a graphical representation. So, let us map our original function which we have been talking about the last couple of classes. This is how you write the map. you always write the map like this with all the cells and marked with zeros and ones on the left hand side for this variable and zeros and ones on the top for these variables, then only the map is complete. This map is also called a Karnaugh map. Karnaugh, after the name of the guy, probably the person who probably invented this. They simply call it K map. Text, you will see this K map being mentioned in textbooks or Karnaugh maps. So, let us apply that function in the truth table that we had originally for f is equal to a plus b c bar, right. Which are the entries of the truth table which were 1 in the output, the row number for 1 I think it was 2, no, you remember A, B, C, this is the truth table. This was a 1, right, B, C bar. This was the original truth table we have been talking about the last few classes and all the examples. So, there is a 1 correspond this row and all these 4 rows, the output. All other rows, the output was 0. So, the output is 0 for the first row, the second row, 4th row, 1 for 3rd row, 5th, 6th, 7th and 8th rows. But we do not call it 1 to 8, we always call from 0 to 7. The reason is very simple. With 3 variables I can have 8 values, but if 0 has been included as one of the values I can go only 7, 0 to 7 or 8 values. So, when you have a number representation, 0 is an essential thing. I can't have a number representation where I cannot represent 0. So, with a binary number 1 with 1 digit or 1 bit of binary, even though there are 2 values possible, one of them happens to be 0, the other one happens to be 1. So, I can only represent a maximum of 1 using a binary bit. If you have 2 binary bits or 2 bits, I can have 4 values, but the first value is 0. So, it is 0, 1, 2, 3. 0 is 0, 0, 1 is 0, 1, 2 is 1, 0, 3 is 1, 1. I can't represent 4 using 2 bits. Since we are going to be binary and we are always have to have 0 as one of the values, we always in digital design and digital system, digital representation, wherever digital things are involved, we always start with 0 and not 1. So, the first entry is always a 0 entry. So, that way I will call this 0th row, 1st row, 2nd row, 3rd row, 4th row, 5th row, 6th row, 7th row. And we also had called it these variations or combinations of the inputs. Each of the input combinations of a truth table are called min terms. So, first min term is min term 0, second min term is min term 1. So, as a symbol for the min term, a small m. And that K map here. So, this is called min term 0, min term 1, min term 2, min term 3, min term 4, min term 5. So, min term 0 to 7 are these 8 min terms possible with 3 inputs. And when it comes to max terms, we talked about max terms also yesterday, we use a capital M for max, small m for min. So, I do not even have to write this truth table. Of course, this one is what we should get finally, this is what we started with. But this is the truth table which we considered and said that this is same as this. We first do a circuit for this, then we said the circuit can represents a truth table of this type, and then we proved yesterday using Boolean algebra that this table can be represented to this function. Now, my objective is to reduce this table again to this using Karnaugh map. Yesterday we did it using Boolean algebra, today we will do it using Karnaugh map. So, I do not need this anymore unless I have at the end to verify whether the result is right or wrong. This is what I should get, we will see whether we get that. So, I have the truth table and I have to represent it in Karnaugh map, map it in a graphical representation in a K map, and you do not even need this truth table. Somebody is going to give you the truth table and then you are going to map it. So, why waste time, because you know what the truth table is all about, all possible input combinations and the combinations for the input for which the output is 1. If that information is called the truth table, you list all the input combinations possibilities and also list those combinations for which the output is 1. So, instead of saying all this in such a big way, can I not simply say this function f has output 1 for m2, m4, m5, m6, m7, because you know what is m0 for 3 variables, it has to be a bar, b bar, c bar or p bar, q bar, r bar or whatever, x bar, y bar, z bar, whatever, x, y, z, p, q, r, alpha, beta, gamma, a, b, c, does not matter. But as long as there are 3 variables, only these 8 combinations are possible. So, what is the point in writing everything in a big table and say this is 1, this is 1, this is 1, instead I am saying this f is equal to minterm 1 m2, minterm m4, minterm m6, m5, minterm m6, minterm m7. For these minterms, output is true or 1. I represent it by a, since it is a sum of product expression, remember each of this is a product term, I represent it by a sigma. So, if I now say my function is, I will remove this now, given function is f is equal to sigma m standing min terms, instead of even having to say m repeatedly. See, our try to minimize having to repeatedly do the same thing over and over again out of laziness or whatever you want to call it, or you want to save stationery or just monotonous, boring. Just do not have to keep on doing the same thing over and over again. So, all you have to say is sigma m means the sum of products, and what are the product terms involved? Are the min terms 2. So, if I give you the function like this, f is equal to sigma m 2, 4, 5, 6, 7, you know the truth table and you know the entries in the truth table for the for which the outputs are 1 and the others are 0. So, my job is to map this into the Karnaugh map, represent into this Karnaugh map this truth table. So, I do not need to give you this, I do not need to give you this, I will give this from here, you should be able to directly come to this, you will directly be able to get this here. Now, in order to help you in the beginning, later on you may drop this, you can write these min term numbers in the cells. This is min term number 0, 1, 2, 3, 4, 5, so that you will not make a mistake in the beginning, and then later on you know that all by experience. So, these are the min terms. My job is to map or represent into this map, on this map the terms for which, min terms for which the output is 1 or true. These are 2, 4, 5, 6, 7, isn't it? So, this is the K map of the function given as this, which is can also be expressed as this, or can be expressed as sum of product as a bar b c bar plus A B bar C bar plus 5 terms we wrote yesterday. Do you understand what I am saying? So, this is the Karnaugh map and this is the function. How do you simplify it, reduce it, so that fewer literals are used and fewer terms are used in the final implementation, the final representation. So, that is where our adjacency rule comes in, because we know the two adjacent cells differ in only one variable. So, we find a 1 in one variable, one cell, and a 1 in an adjacent variable cell. Adjacency works left to right, top to bottom, end to end, not diagonally. Adjacency does not work diagonally, you have to remember that, there is no adjacency diagonally. So, anywhere I find a 1 top to bottom or side to side, I will try to combine these two and find out which is the variable which is appearing in one cell as a complement and the next cell as a true. In one cell will appear as B bar, the next cell will appear B, then B goes because of the A plus A bar is equal to 1 or B plus B bar is equal to 1 relationship. That is easy to identify. For example, these two cells, A appears as 0 here, 1 here. So, this cell is, so I will now remove this truth table, we do not need this anymore. So, if I take these two cells and connect it like this is equal to, just I do not have to do all this later on you will be able to read it directly from the map. Now, the first time I am going to write it as this is A bar, B, C bar, this corresponds to B, this corresponds to C bar, this corresponds to A bar. So, I write it as A bar, B, C bar, and this corresponds to A, B, C bar. Correct? These two together can be written like this, and what is common between these two? A bar is A is B is common, B is common and C bar is common. So, B C bar is common, take B C bar using that distributive property, say A plus A bar is 1, and since A plus A bar is 1, so known identity, this is same as so these two cells can be merged or combined into a single term of B C bar. Each of these cells have 3 terms, 3 variables. I have knocked off one of the variables. So, 3 variable terms have been reduced to 1 2 variable term. That is the simplification procedure. That is nothing very great about it. All we have done is identify the adjacent cells where ones are marked and found out which of the variable was constant in these two cells, which is variables are changes between these two cells, and changing cell variable is removed. That is all. So, you do not need all this algebra, because you know B is constant between these two, C bar is constant between these two, A goes from 0 to 1. So, since A goes from 0 to 1, you can write this without A with B and C bar. So, you do not need this algebra, I just wrote it for your convenience for understanding the first time. Now, let us extend this argument to these two and these two. These two will have A common, B common, C varying. So, I can write this as AB. Between these two, A is common, B bar is common, C changes. So, this is these two, if I write together, it will be A, B bar, because A is common between these two, B bar is common between these two, C changes from here to here, has to be knocked off. Between these two, A is common between these two, B is common between these two, C changes from here to here. So, C gets knocked off. So, this is AB. But again these two cells and these two cells are adjacent. Here it is B bar, here it is B, A remains constant throughout. So, instead of doing it in 2 steps, I can group, instead of each time grouping 2 ones and then combining them again one more step. I can group also 4 ones at the same time. So, these two can be combined to the one group in which it is A B bar or A B which is equal to A. I do not have to do this way step by step, I just showed it to you how to do it, showed it to you how it works, but you do not have to do it this way. All you have to do is to see that A is constant throughout this 4 cell, across the 4 cells A is common, B changes from 0 to 1 across, C changes from 0 to 1, 1 to 0. So, both variables, none of these variables B, both of these variables B and C, or neither of these variables B and C remain constant throughout. So, they both get knocked off. So, it is not necessary to knock off only one variable, you can knock off 2 variables, you can knock off 3 variables. In order to knock off 3 variables, you need 8 ones in a group. So, if you have more number of ones in a group adjacent cells, it is better for us because we are going to simplify better, our reduction is going to be more. So, that means without going through all this algebra, all this background theory, if I give you this map now, same map, all I said was 1, 1, 1, 1, 1. I will simply do it, combine this and combine this. This combination I will write it as A, this combination I will write it as B C bar. So, my final function is the OR combination of this or this. C bar. This is our function to start with, we started with. So, that means Boolean algebra can also give you, I mean K map can also give you the simplification that Boolean algebra gives, but here you know that I have exhausted all ones. How do you know it is done? I have exhausted grouping all ones, no individual one stays out. Of course, if it stays out you have to write it separately, and we have also always considered the largest possible groups of 1. There is a group large group of 4 ones possible, here there is a group of 2 ones possible. So, wherever possible you have taken the largest possible group in that particular group. So, there is no question of doing it better than this. So, this way you are more confident of your final output compared to Boolean algebra, where you might have or might not have used an identity which should have been used. There lies the difference between Karnaugh map method and the Boolean algebra, but Boolean algebra is what we have used finally. A plus A bar is 1 is Boolean algebra. It is not as if it is some new technique or new, I will not say new theory, it is a technique maybe, a procedure may be different, but not the theory. And now you can extend this to 4 variables. 4 variable will have 16 cells, 2 variable here, 2 variable vertically, 2 variable horizontally, and you can do like that. We will take an example of 4 variables. So, this example, simplify Boolean, simplify, or I will not even say simplify, minimize I will say, because I want to get the minimum value, minimize using K map the function f. I can now give the variable of any function variables. For a change, we will go from ABC, PQRS. Function of 4 variables P, Q, R and S, which is true for the following min terms. I am going to write arbitrarily, I am not having any particular function in mind. When you put sigma m, The following minterms are having 1 as the output or true as the output, and rest of the minterms are having 0 as the output. That is what we write the sum of product representation in minterm form. So, let us say 0, 2, 3, 7, 11, 13, 14, 15. I just write it without even thinking about it. We will see what comes. It is an arbitrary example. No specific system I have in mind, no specific circuit I have in mind. So, I have a function PQRS, a function of PQRS 4 variables, and if you write a truth table, you will have 16 rows. And this 16 rows or 16 minterms. Minterm number 0, minterm number 2, 3, 7, 11, 13, 14, 15 have true outputs or 1 outputs, and other minterms, namely 1, 4, 5, 6, 8, 9, 10, 12 have 0 or false as outputs. For such a function, I wanted to do a Karnaugh map and minimize it, reading it by combining the ones as effectively as possible, write the minimum possible expression, minimum sum of product, MSP, minimum sum of product, not sum of product expression, SOP sum of product, which is non-minimum. So, there is a canonical sum of product, which is the standard truth table representation. Then a sum of product is anything which is having some relationship, product relationship. Minimum sum of product is what you cannot reduce further as a sum of product expression. So, let us do the Karnaugh map. We will have 4 variables. PQRS, 16 cells must be there. This is the map, K map of 4 variable K map. Zero zero, 0 1, remember 1 1 and then 1 0, because same argument that we had earlier for BC on the horizontal scale will now apply to PQ on the vertical scale. I want only one variable to change from here to here. So, only one variable changes. If I had put 1 0, both variables would have changed. We do not want that situation, then they are no more adjacent. Two cells are supposed to be defined to be adjacent only if they differ in one variable. If they differ in more than one variable, they are not adjacent according to the adjacency relationship. Even though physically you may put them together, they do not become adjacent. So, this is minterm 0, 1, 2, 3, minterm 4, 5, 6, 7, minterm 8 will start here because of this 1 1 comes later than 1 0. So, 1 0 will have minterm 8, 9, 10, 11, 12, 13, 14, 15. This is the 4 variable Karnaugh map, which is standard, whether it is variables are A, B, C, D or PQRS or X, Y, Z, W or whatever, alpha, beta, gamma, delta. Now, what are the minterms for which the output is true or 1? Those have to be mapped onto this graph. These are 0, 2, 3, 7, 11, 13, 14, 15. Later on, when you start doing this a few more of these exercises, you will drop these minterm numbers, so they will become less cluttered, become clearer map. Now, I put it purposely for you to get used to this. So, you can remove all this later on, so you will not see those. Now, we have to combine them, try to group them, see as many ones as possible at a given in a given group, but they should all be adjacent. I can straight away see a group of 4 ones, 1, 2, 3. You always start with the highest, largest possible ones, largest possible group and then come down. do not start with the smallest number, because sometimes the smaller group may get submerged into a larger group later on. So, start with a larger group. The idea is to combine all the ones, but you can combine a one more than once. Remember the Boolean algebra? Yesterday when we tried to simplify it using Boolean algebra, we used the same term twice, because A and A is A or A is A. So, I can use the same term twice, no problem, but I should not leave out anything. Everything should be included, but it is alright to include a particular cell which is asserted as 1 more than once, does not harm us. In fact, it will help us sometimes. So, first group of ones is this, right. I will call this 1, because there is no space here. I will write later on 1 is. Then we have these two ones, there are 4 ones available here, all of them will be combined. I can't see this one being combined any way other than this, because all other adjacent cells are blank. So, this has to be combined this way. So is the case here. Correct. Here though, I do not have to combine it this way, because this cell is adjacent to this cell, because this is 0 0 0 0, this is 0 0 1 0, or changes from 0 to 1 between these two cells 0 and 2, or changes from 0 to 1, whereas P, Q and S are remaining as 0 0 0. So, cell number 0 and cell number 2 are adjacent, even though they are physically not adjacent. That is what I am saying. Physical adjacency is different from logical adjacency we are talking about here. We are talking about logical adjacency. So, that way I do not have to mix this here, because since this is going to be combined, this is going to be combined, this has not been combined anyway. So, I will combine these two. So, I will call this 2, I will call this 3, there are 4 terms. There are now 4 terms of groups of ones, and each of them I have to write a logic expression, sum of product expression. Then my final output F is sum of all these product expressions, SOP, sum of product, minimum sum of product. So, what is 1? 1 F is 1 is this variable P and Q change all over. So, you have to write only this R and S are 1. So, RS. So, 1 corresponds to RS. So, 1 is RS. 2 would be PQ are 1 1, they remain 1 1 here and here. So, they have to remain in the expression. Here S is 1, here also S is 1, whereas R is 0 here, R is 1 here. So, R changes from 0 to 1 between these two cells. So, R gets knocked off. R gets knocked off from this cell to this cell, whereas S remains 1. So, 2 is nothing but PQS, PQS. PQS. 3 same argument PQ, R remains 1, S changes from 1 to 0, S gets knocked off, R remains. So, 3 is PQR. Finally, the last fourth one is PQR 0 0, R is 1 here, R is 0 here, R is 1 here, R gets knocked off, S remains 0. So, it is P bar, Q bar, S bar. So, that means my final expression is RS plus PQS plus PQR plus P bar, Q bar, S bar. each of these terms P, Q, I mean each of these terms 1, 2, 3, 4 which are product terms which combine to become sum of product later on, each of them is called an implicant, prime implicant. An implicant is any group of ones. Suppose I write a term, I will not do that, supposing I did between these two ones, that means it is RS11 P1. So, if I write PRS, PRS will mean these two cells, cell number 11 and 15. Cell number 11 and 15 if I combine together I will write it as PRS. I will not do it because I am covering a larger group of ones, 4 ones. So, there is no need to do this. Suppose I did it, it is called an implicant, it is not a prime implicant. A prime implicant is a group of ones, the largest possible group of ones in that particular context. For that group you cannot find a larger group. An implicant gets submerged into a prime implicant. A prime implicant is the largest possible group of ones that you can find for a given group, and out of all the prime implicants, any prime implicant which is essential for the final representation. I told you two things, we have to make sure all ones should be covered irrespective of the fact that one can be covered more than once. For example, this one has been covered 3 times, this was covered along with this, covered along with this, so that is okay. But in each time we have included at least one cell which had not been combined earlier, is it not? When I wrote this number 2 term, this one has been included new. When I wrote 3 term, I included this one new. So, an essential prime implicant, so I defined an implicant I defined an implicant, I defined a prime implicant, now I am defining an essential prime implicant. In an essential prime implicant, there will be at least one or one cell which has not been covered in any other prime implicant. There should be at least one cell or one of assertion true value which has not been included in any other group. Such a prime implicant called an essential prime implicant. In this case all the 4 are essential prime implicants, because this one and this one cannot be covered and these 3 ones cannot be covered other than this group. This one will not be covered other than this one will not be covered other than this, and these 2 ones will not be covered in any other way. So, in here all the 4 prime implicants are essential prime implicants. Sometimes occasionally we will get non-essential prime implicant. Supposing you have different ways of combining a 1 in 2 groups, you can combine this way or that way, both of them will lead to the same result or similar results. Such a group is called a non-essential prime implicant. That means there is more than one way of combining a 1 which is not covered otherwise as a essential prime implicant, but one of them is essential, otherwise that one will be left out. Supposing I have 2 different ways of combining a particular 1, I have exhausted all ones in a group, in a map, all entries in a map, all cells for which the output is true I have exhausted except one. There is a 1 hanging out which has not been covered yet in any essential prime implicant or any prime implicant. Now, I want to combine this 1 and I can find several possibilities or at least 2 possibilities, but both of them, one of them may be required, the other may not be. If I take this, the other one is not required, if I take the other one, this is not required. So, this is a non-essential prime implicant. That prime implicant is important, it has to be covered, but each of those two prime implicants which I will get by combining this one with two different ways are called non-essential prime implicants. So, it is not necessary to include all non-essential prime implicants in the final output, it is only necessary to include as many non-essential prime implicants as required to cover all the ones in the map, whereas essential prime implicants, all of them should be covered in your final output. We will take an example of a non-essential prime implicant, how a particular one can be covered in different ways, and how only one way may be required and all other ways may be redundant. That will tell you more about a non-essential prime implicant. We will see it in the next lecture.